Bien, hola. Eh, para mí es un gusto presentar a Pablo Ocal de la Universidad de Texas. Él nos va a hablar acerca de la cohomología de Hochschild de productos tensoriales en inglés sería Hochschild Cohomology of General Twisted Tensor Products. No sé cómo decirlo en español. Y bueno, un gusto tenerte acá, Pablo.
Muchas gracias por tenerme. Y sí, son productos tensoriales torcidos, creo que es el cómo los llaman. Y disculpadme que haga la charla en inglés. Después de casi ya 10 años de haciendo matemática en inglés, me resulta súper complicado volver al español. Así que quiero disculparme con antelación. Pero por favor, preguntas en español, responderé en español y si me tomo una palabra en inglés, de nuevo lo siento. So yes, I'll be talking about Hochschild cohomology of general twisted tensor products. And everything I'm going to talk about today is joint work with the Tekin Karadag, Dustin McPhate, Tolulope Oke, and Sarah Witherspoon. And I want to divide this talk into 5 sections. So first of all, I'm going to give you like an introduction, like why do I care about Hochschild cohomology and twisted tensor products. Then I'm going to be talking about a few things that probably everybody knows on Hochschild cohomology, and then a couple of new techniques that were recently developed. Then I'm going to define what a twisted tensor product is and give you some intuition on that and how resolutions of these guys work. Finally, I'm going to give you the results that we found and some applications of our work. So let's get started. So throughout this talk, I'll be considering unitary associative algebras over a base field, and I'll be calling those A. And K doesn't need to be a field, but if it's a field, many things are simplified. So what do I care about the Hochschild cohomology? So there are a few ways of seeing this, but my favorite one is that the Hochschild cohomology encodes some infinitesimal information about our algebra. So what do I mean by that? So let's look at the first few lower degrees of this Hochschild cohomology and see what they are. So in degree 0, we just have the center of the algebra. Which at first approximation, it may not look much as infinitesimal information, but after all, it's just the degree 0 term. In degree 1, what we actually have are the derivations of A. And these are not just the normal, like all the derivations, these are the outer derivations, right? So like the derivations that actually matter and that are not coming from within our algebra. So this is a more legitimate way of seeing that this is actually some infinitesimal stuff going on. But everything becomes much more clear when we look at the second Hochschild cohomology. And I will be not giving you an explicit construction of this, but just for the sake of it, let's say that these are the important infinitesimal deformations. And what I understand by deformation here is that I'm using my multiplication of A and I am perturbing it by a tiny bit, like some form of Taylor expansion of my multiplication. And by this small perturbation, I am looking at the new algebra that I obtained. And these important infinitesimal deformations are the ones whose final algebra structure after doing all of these perturbations are not isomorphic to the original one. So those are like the ones that we should care about. So this is why I like Hochschild cohomology, because it encodes this type of information. And what are twisted tensor products? Now, we denote them by the tensor product with a sub tau, and these guys were defined by Cap Schilch. And Manzura when they were studying non-commutative geometry, and more specifically tutori, and they proved that whenever we have an algebra over a field that has an underlying vector space structure, that is given by the tensor product of two algebras. Then this original algebra is actually isomorphic to a twisted tensor product that we denote this way. So there are a surprisingly number of applications of twisted tensor products, and nowadays they just show up everywhere you look. Specifically, they show up with relation to operator algebras, because they are very much related with cross products of C-star algebras and skew products of C-star algebras. They also show up in algebraic topology a lot when we're considering field theories. And with respect to that, one of my favorite applications is in quantum symmetries. Because it's a gigantic generalization of structures like super Lie algebras, for example. So this being said, let's talk about some things that we know and some things that maybe we don't know that much about Hochschild cohomology. So even though there are many experts in the audience, I can't really get away of talking about it without defining it. It just feels wrong. So let me just recall that the Hochschild cohomology algebra is just the X groups. And let me introduce some notation that I'll be using. My AE is the enveloping algebra of A, and everything that we'll be seeing will be considered as modules over this enveloping algebra, or alternatively bimodules over A. And in particular, we will be considering a very specific bar resolution over this modules. So yeah, so if we add all of this up, then we get the full Hochschild cohomology. Good. So this is a pretty clean definition, but this very much relies on K being a field. So if our algebras are over something that is not a field, then we can no longer say that these are X groups over an enveloping algebra. Something a bit more complicated happens, but you can still do a lot of work. So let's just, for example's sake, stick to K being a field. And now let's try and compute this, right? So the usual way that we compute this is through the bar resolution. Historically very important, and we can define all the operations there we are interested in through it. So since there are many bar solutions and not all of them were created equal, let me tell you which one we fancy. So as I mentioned, I will be considering all modules over this enveloping algebra. And these will be a few tensor products of my original algebra, namely n plus 2. This will be in position n. And the module structure, or the bimodule structure over A, will be given by tensoring on the outermost factors. So we have n factors in the middle, we have 2 lefts on the outside, and then we multiply on the outside. And given these modules, then the bar solution is just putting them one after the other. I think I want to start at 4, yeah. So we have 4 tensors, then we have 3. Then 2, then 1. I wanted to start 4, but I started at 3, that's okay. And here the differential, let me give me some space. But here the differential doesn't have like a cyclic component that sometimes we see it in the bar solution. Here we just take n plus 2 copies of the algebra, and then we successively remove tensors, and we just multiply what's left. And we add a sign depending on which tensor we removed. And so this complex equipped with this differential turns out to be a resolution. So this is just one, maybe the is not the best name for it, is one of the solutions that are called bar resolutions. And the reason that we fancy this specific one is because when we have different families of algebras, right? So for example, if you have causal algebras or monomial algebras, there is often a specific resolution tailored to them, right? So if you have causal resolutions, then we have like the causal algebras, then we have the causal resolutions. If we have some complete intersections, we can use finite free resolutions to have easy access to them. And if you have like a monomial algebra, so for example, quivers, modulo sum relations, often we can use the bar cell resolution to work with them. And the reason that we like this very specific form of the bar resolution is that we can embed some other very specific form of the causal resolution within it. So let me tell you a bit more about that. So let me use a different color maybe. So if now I am in the case where A is causal, then we can take a resolution that will look very much like it at the very beginning. So I don't know if going backwards is going to be ideal, but let's try it. So here is everything is going to be the same thing, but now A being Kosul means that I can put A as a quotient, some tensor algebra module, an ideal generated by some relations where R is going to sit in 2 copies of my tensor product of the vector space that is defining my causal algebra. So having this, then we can do something a bit sneakier. So since here we have 3 copies of A, we can change the middle one to be a copy of V. And V is naturally lying inside of A. So here we can consider, instead of 3 copies of A, 1 copy of A, V in the middle, and then another copy of A. And for 4 copies, we can do the same thing, except that now, instead of considering 2 copies of V, we can consider R. And all of these are still bimodules over my algebra, because I still have 2 copies of A on the outside, so I can still just multiply by A, and what happens in the middle is not affecting our module structure. Good. So how do we keep on pushing this backwards? So in general, when we are in n bigger than 3, then we define Kn A. We define this to be just 2 copies of A on the outermost factors, and then in the middle, an intersection of my V's and my R's. And doing this, I can just extend this complex backwards. And I say complex, and I haven't given you any differentials yet. Well, precisely by construction, we can just put the differentials to be formally the same. I'm just using, again, this exact same formula. But maybe instead of my elements being in A, I need to see them in A through the canonical injections that we have. Good. So this is the precise reason why I care about this explicit form of the Barre solution, because we can very easily see another specific form of the causal resolution inside it, right? Like there are very canonical maps from the causal resolution to the Barre solution. And here these maps are extremely explicit. And this will come into handy in the results part of our work, when we will actually see that if we want to do some explicit constructions, then it is very helpful to have the causal resolution explicitly inside our Barre solution. So why would the causal resolution be relevant in this case? Well, we want to do the usual game of having some cup products and brackets defined in the Barre solution, and then translate them to other resolution, right? So that's
sorry, Pablo. The quick way of defining those Kn is taking the Kosul dual of A, right?
yes, absolutely. Yeah, that's exactly what I'm doing. I am just sweeping all that under the rug. But yeah, there's definitely a causal dual that can be found using this. The other way, there is definitely a way of finding these using the causal dual. Yeah. I'm just interested in having everything super explicit in terms of A, and that is why I'm using this explicit formula. But yes, you're absolutely right. Okay, so I was saying that the final goal, right, is to understand the Gerstenhaber bracket on some Hochschild cohomology. Right, that is the usual goal that we have when we deal with Hochschild cohomology. So how can we do this using this explicit formula for the causal resolution? Where does this come into play? All of this is very much motivated by the work of many people that had recently culminated into Volkov's paper. So let me give you a diagram of what happened. So I think it was like around 2016, 2017, Negron and Witherspoon they found a way of explicitly constructing the Gerstenhaber bracket. And what they used are causal like conditions on some resolutions.
So this is the paper where they take basically as a quasi-isomorphic subcoalgebra of the bar construction, right?
Pero no te escuché el principio de lo que dijiste, Pedro. ¿Puedes repetir?
This is the paper where they take a quasi-isomorphic sub-DG coalgebra of the bar construction and just use the co-product on that, right?
I think so, yeah. So yeah, absolutely. That's what Pedro said, is what I mean by just causal like conditions on resolutions. And they use this to give an explicit Gerstenhaber bracket. And then very recently, about a year ago, I think, maybe two, Volkov massively generalized all this. And what he did is he translated the conditions that Negron and Witherspoon required on the resolution to cochains. So he reinterpreted those conditions, and instead of putting them on the resolution, he just put them on the elements of the cochains when you just take any resolution. This is not where I wanted this. I just want to put Volkov here. This, importantly, is in any resolution. So then he uses this, very much inspired by Negron and Witherspoon's work, to again give an explicit Gerstenhaber bracket. So this is what is going behind the scenes. We are using rather explicitly this construction for our work, and we're expanding the techniques that they introduced But behind the scenes, I cannot help but comment on Volkov's generalization. Like, it is extremely important, even though we don't explicitly use it. So this being said, and with the goal clear, right? Like, we want to understand Gerstenhaber brackets and some Hochschild cohomology. Since I'm talking about twisted tensor products, this will be Hochschild cohomology of twisted tensor products, hopefully. So let's not jump to what's the actual definition of a twisted tensor product. So this is one of the most natural constructions that you can think of, maybe. Twisted tensor products are generalizations, essentially, of the usual tensor product to a non-commutative setting. But as I mentioned in the introduction, it turns out that these are just not generalizations, they're gigantic families of algebras. And in order to construct the tensor product, we require two algebras, A and B, and they will be algebras over a field, and we will require a twisting map, which will be a way of permuting B and A. So this twisting map is just exchanging B and A. Since we're using tensors, then this will be required to be linear. And since we're exchanging them, we will require this to be bijective. But just a bijective linear map is not too good. It doesn't give us much information. So what we actually want is for this map to respect the structures of B and A, right? So B and A are algebras, they're unitary algebras. So if the twisting map is to be well-behaved with respect to B and A, the first thing that we want is for them to respect the unit. So if we twist the unit of B past any element of A, then the unit should be maintained. And similarly, if we twist the unit of B, excuse me, past any element of A, the unit of B should be maintained. And similarly, if we twist the unit of A, this should also be maintained. But this is not telling anything about the multiplicative structure of B and A. So we would also want the twist to respect the multiplicative structure. Namely, we just want twist and multiplication to commute. So a very natural way of encoding that is just putting it in a diagram. So to multiply, we need 2 copies of A and 2 copies of B. So the smallest possible diagram that we can make, making twisting and multiplication commute, will begin with 2 copies of B and 2 copies of A. And we will first twist, and the only way we can twist is in the middle. Then we shall twist again, and we can only twist the outermost factors, and then we get we finally twist yet again until we can no longer twist. So this is all the twisting we can do, and then we just multiply them. But of course, we can do this directly. We can first multiply. And we can then twist. And we require that this commutes. Right? So to be extremely explicit, here we are twisting. Here we're multiplying, and vice versa. So this is what I mean by our twisting being well-behaved. And this will come up a number of times in the next few minutes. I will require that almost everything that I talk about is well-behaved with respect to a twist, meaning that whatever algebraic structure I'm talking about, it is compatible in a similar way as this to the twist. So once that we have a twisting map that is just satisfying the bare minimum of being compatible with the units and the multiplicative structure of our two algebras, then we can construct the twisted tensor algebra. This will just be A tensor B as a vector space with multiplication. The natural thing that we all want to do, right? So if we have one copy of a twisted tensor product B, and we have another copy of a twisted tensor product B, the multiplication just should be, ideally, permuting middle terms and then multiplying. So by defining such an object, it turns out that this twisted tensor algebra is actually an associative algebra, and it's also unital. So if my title is not misleading, then what I want to do is understand the Hochschild cohomology of this guy.
So in your case, you want both A and B to be cosul to start with, or?
Not just yet. That is precisely where I was getting. So sometimes we can obtain information about the twisted tensor product when we know information about A and B. So if A and B are cosul, the twisted tensor product sometimes will be cosul, sometimes not. But if our algebras are cosul, we would like to have some cosul-like resolution on a twisted tensor product B. And that is one of the things that we did. So there is a natural way of finding resolutions of a twisted tensor product B, but those resolutions are not always well behaved. So they may not be projective, for example.
Yes. Sorry, just a question. I mean, if you're going to deal with this later, perhaps I'm asking something that I ask later, but isn't it always true that if both of them are cosul, then the twisted product is cosul? Like, this is true for operas, so I don't see how it can't be true for algebras that at least have a nice weight grading. So if you did this whole construction, but you did it with operas and you did the whole same thing, then that any well twisted product will be cosul as soon as the factors are. Well, yeah.
So I do not know about operas, and I cannot think of an example off the top of my head when this
or algebras.
Happen. Yeah, I cannot think of an example, but I'm very much inclined to say that there may be an exception. but I
Okay, I'll
cannot
just
guarantee
think about it. I mean, it's just that for algebras, you have things in sort of in just one degree, where operas usually don't have things. So there may be some like issues, but yeah, okay.
So if your twist is very nice, so for example, it's strongly graded twist, then very likely, and I will get to that in a minute. So if your twist is strongly graded, very likely this construction is causal if your factors are causal. But if your twist is like
you need things to respect the grading. I agree. Yes.
Okay, then yes.
Yeah.
If the grading is respected, I am almost positive that the end result is causal. Yeah.
Right.
But being strongly graded is more than respecting the grading.
It is. It is a bit more. Yeah. But yeah, like if it respects the grading, I am inclined to say that the end result may be causal. If it does not respect the grading, I'm very much inclined to say that the end result is not causal, but I cannot guarantee, I cannot give you a counter example, and I cannot give you a proof of either of that statements.
Perdón, una pregunta todavía más previa. Si A y B son, por ejemplo, semisimples, ¿sabemos si el producto torcido es semisimple otra vez?
Yo diría que no. Porque el twist puede ser complicadísimo y puede meter factores que afecten a la semisimplicidad, pero no te lo puedo garantizar tampoco.
Porque un álgebra semisimple es cosul de manera idiota si uno simplemente piensa que está concentrada en grado cero, entonces ya ahí estarías tensorizando dos cosas cosul y saliendo del mundo cosul. Se me ocurre que ese es el tipo de cosa que se puede romper, ¿verdad? Hay como... como que es mucho más básico que...
si el twist introduce términos... Yeah. Creo que Mariano va a decir un ejemplo.
A very simple example is the first file algebra. It is the twisted product of two polynomial rings in one variable, and it's not causal.
Justamente porque te está metiendo un bueno, pero ese no es graduado, ¿no? Ahí hay un problema de grado.
O sea, justamente el ejemplo de Mariano lo que dice es que si pones términos lineales, que es lo que a veces hacen estas leyes distributivas, estás arruinando la cuadraticidad, ¿no?
Sí, sí, metes grado cero y no preserva el grado. ¿No? Sí.
Claro, pero eso tiene el tema de que rompe el hecho de que la álgebra sea cuadrática y entonces todavía podés hacer esta cosa tipo Polishchuk y Postselsky que dicen que un álgebra es cosul si tiene una filtración tal que el graduado asociado es cosul graduado. Pero es algo todavía más básico, ¿no? Que es que no tiene sentido decir que un álgebra es cosul si el álgebra en grado cero no es por lo menos semisimple. Entonces
estoy seguro que si agarrás álgebras del tipo K por K y haces productos cruzados, encontrás cosas que no son cosul.
Sí, totalmente. Porque estos tau pueden ser increíblemente horrendos.
Sí, son horrendos en general, sí.
Justamente, ¿no? Porque que algo tenga de su espacio, que un álgebra tenga el subespacio de A tensor como subespacio lo mismo que A tensor B es como una condición muy, muy débil. Entonces, los tau pueden ser casi cualquier cosa.
Sí, y de hecho... Pablo, seguiste, no te quería interrumpir.
No, eso solo... Gracias porque me había cruzado con esto hace tiempo y me quedó dando vueltas esa cuestión de si era cerrado para qué tipo de propiedades.
Sí, o sea, mi comentario al principio, Pablo, es que lo que yo quise decir fui impreciso en lo que dije. La ley distributiva o el twisting tiene que venir de un twist en las variables y P y W, digamos. Si haces un twist general, obviamente con operats cosul, no te va a quedar cosul, pero si haces un twist que depende solo de las variables y lo extendes a la álgebra, a las álgebras, en ese caso, bueno, es entre comillas fácil ver que te queda cosul. El caso de operats es un paper de Martin Markle, pero
Si solo depende de las variables, pero no estás añadiendo ningún término de... O sea, si estás preservando el grado, ¿no?
Claro, porque quizás
Vale.
eso es lo que quieres decir con strongly graded. O sea, si A está generado por V y B está generado por V, entonces... o W, perdón, no quiero confundir V corta y V larga, W. Entonces, uno define algo de V por W a W por V y lo extendes al producto tensorial, ¿no? Entonces, en ese caso sí es fácil ver que te queda COSUL. Pero claro, los ejemplos que estamos dando ahora justamente dicen que el caso general no anda ni cerca.
Sí, gracias. Sí, desde luego. Si tienes términos que no preservan el grado, puede ser muy caótico. Pero sí, bueno. So indeed, the goal of this is to understand this Hochschild cohomology, or the Gerstenhaber bracket, more explicitly. And like we just discussed, one of the ways that we do so is by just having like a resolution of A. So for example, if A is COSUL, we have the closed resolution. A resolution of B. If B is COSUL, we can have one. And then we like sort of glue them and stick them together. And we get a nice resolution for a twisted tensor product B. And under some conditions that are not that restrictive, we can explicitly give you a bracket of this twisted tensor algebra. So what are some of the conditions that we may require to build this? So as I foreshadowed, in the same way that we have a compatibility of algebras and a twist, there is such a thing as a compatibility of modules with respect to a twist. So just briefly, definition / remark. So for modules over the enveloping algebra of A and the enveloping algebra or B, there are notions of compatibility with the twist. So namely, if we just have modules, then the compatibility would be something as like the twisting and the modulation commuting, which gives a very explicit diagram of the same type that we saw before. And another compatibility condition is that the twisting and the multiplication commute, because this twist will now be permuting the module and some of the algebras. So the compatible permutation also needs to respect the multiplication of our algebras, after all. And if we are compatible, so under this condition, the tensor products can be given a natural structure of a bimodule over the twisted tensor algebra. And in fact, we have not only compatibility of modules, we have also compatibility of resolutions. So this extends actually. So there is such a thing as the resolutions being compatible, and essentially means the whole thing, right? Like we have modules that need to be, each of them compatible, but then we also need to have a way of, if we have two resolutions, of just like completely flipping them. That's essentially what this compatibility means. And under these conditions, we can actually find resolutions of the twisted tensor product. And that's a theorem of Shepler and Witherspoon. So we can find a resolution of our twisted tensor product coming from resolutions of A and B. And in fact, if the resolutions P and Q are projective, then the resolution that we obtain is also projective. So the way that this is actually constructed is basically taking a total complex. That's essentially what's happening. And once we have the total complex and we just merge all the terms in each degree of the resolutions, using the twist, we can just permute them and like successively exchange them with one another. And then we find that there's like some first terms that is quote unquote resolving the A, and then some other terms that are quote unquote resolving the B. And then what's happening in between them it's what's encoding the twist. So what are examples of this? Well, the bar resolution is always compatible. So the bar resolution can always be found, can always be used, excuse me, to find resolutions of twisted tensor products. So we can take the bar resolution as an input of the theorem, and it satisfies the hypothesis. And then the causal resolutions when tau is strongly graded, we do need strongly graded in general. That also yields compatibility. And as Andrea was saying,
what does strongly graded mean there?
It essentially means that I not only preserve the grade, but I preserve the individuals, or not equal, contained in. My degree is preserved in every term. So if I have something that has degree I and j, I go to degree j and I, which is a bit more than just I plus j to I plus j.
Thanks.
Yeah, so this is like, those twists are really good. Like that is much more restrictive than one would think at first hand. And in fact, it turns out that when you have a strongly graded twist with causal algebras, just preserving degree 1 almost automatically means that you preserve all degrees. So this is a very restrictive condition. So with all of this in our pocket, let's finally look at some of the results. Yes.
A strongly graded twist is completely determined by what it does to generators then?
All of them. All twists are determined by what they do to generators. But if our algebras are causal and we force that we have strongly grading in the first degree, many times that forces all of the degrees to be preserved in this way. So what I mean is that, let me put that on quotes. So let me say that B is going to be is contained. So many times just having quote unquote strongly graded in degree 1 forces everything to be strongly graded. So yeah, it's much more restrictive than one would ideally like. Okay.
Y perdón, una pregunta. En el caso 1, cuando uno tensoriza y tuerce las resoluciones bar, ¿lo que queda es la resolución bar del producto tensorial o isomorfo a eso?
Se puede construir un isomorfismo de complejos de cadenas. Un isomorfismo de complejos de cadenas que satisface it lifts la multiplicación canónica que está pasando en grado 0. Sí, eso es precisamente una de las condiciones que nosotros usamos. Sí. Y eso también pasa.
Pero no queda exactamente... no queda igual, digamos.
No queda igual. Pero queda isomorfo de una manera súper fuerte.
Ok, gracias.
Entonces, resultados. Number 4 results. So what we found is that when we pick any two resolutions of A and B, and projective, because we actually want to do something with them. And we don't require anything on them. What we do require is that when we do this construction of Shepler and Witherspoon, and this is nice. And by nice, I mean something very similar to what Negron and Witherspoon required, with the exception of some additional conditions. So by nice, I mean a co-unital DG coalgebra. That's it. So if this is a co-unital differentially graded coalgebra, and there is a nice, and I'll get back to that nice in a minute. A nice chain map that relates to the question that I was just asked. So if my chain map goes from the twisted tensor product of two resolutions, and then I take the total complex over the twisted tensor algebra with itself, and it goes to, again, three other total complexes. So if we have a nice co-unital DG coalgebra, and we have a nice chain map that is an isomorphism satisfying that it lifts the first canonical multiplication in degree 0. So this is not only a chain isomorphism, but it also lifts a very specific map that we have for degree 0. We have a multiplication, and if it lifts that, then we can give you an explicit formula for the Gerstenhaber bracket. Which is pretty important. Like we have some explicit construction, and by explicit I mean, here you go, it's equal to this. Like I'm not giving you an algorithm to find it. I'm giving you like an exact equation of how the Gerstenhaber bracket looks like. So this is like a something in between of what Volkov and Negron and Witherspoon did. Like we do have some conditions on our solution. We do have some additional, and our conditions are weaker than theirs. We also have like some conditions on a chain map that is not related to the resolutions in principle. And like the enabling factor, so to speak, of our construction and what allows us to give this explicit formula is that by using the twist, we can just track, just like you draw a gigantic diagram and you fill it in, and just like by induction, you have that using this chain map isomorphism, you can trace where every single element goes, and that gives you this explicit formula. And this has as input both the bar resolution and the causal resolution, right? So let me, since I am almost out of time, let me make an asterisk here. And let's say that these two resolutions can be used as input. So in fact, our formulas are applicable in full generality, right? The bar resolution always exists. So it may be hard to find, but we always have an explicit formula for this Gerstenhaber bracket. So that was very exciting. And now in the 2 minutes that I have left, let me really quickly tell you some of the applications. And something that I should mention, not only because I'm being recorded, is that this is very much based on work by Grimley, Nguyen, and Witherspoon. Okay, let me check that I'm not forgetting any of the references. I am not. Fantastic. So then some applications. We applied this to compute the Gerstenhaber bracket structure on the Jordan plane. And this had previously been computed by Lopez and Solhar. But they used completely different techniques. They used the Yannick resolution, and they used specific methods for derivations. So the Jordan plane will have cohomologies in degree 0, 1, and 2. So they used techniques for the derivations to compute the higher brackets. And we use completely different methods. Like we just apply our formulas, and that's literally it. So by let me rephrase this. The reason why this is important is because the Jordan plane is not strongly graded. So the Jordan plane is isomorphic to this twisted tensor product, where tau sends y tensor x, x tensor y, plus x squared tensor 1. So this is not strongly graded because of this. So we cannot use the theoretical framework, right? Because like our causal resolutions required the twist to be strongly graded. So instead, what we did is we used that we can trace through all these commutative diagrams. We can trace what the causal resolutions look like when we apply the twist. And then we found a co-unital DG coalgebra on the twisted tensor product of the causal resolutions. We found an explicit isomorphism that we required for this theorem. And then once it proved that we had all of these conditions, then we can just safely apply the theorem. And we know that the Gerstenhaber bracket is going to be given by an explicit formula. And some work in progress is looking at what happens when we have some different twists, right? Like we're looking at graded twisted tensor products of planes. And this being said, I am a minute over time. So, thank you for your time.
Muchas gracias, Pablo. ¿Alguna pregunta? ¿Comentario?
Yo quería preguntar, ese álgebra que escribiste al final, digamos, no tenés, bueno, tenés, claro, la única relación que tenés es esa, ¿no? O sea, la podés presentar como el álgebra libre en dos generadores que cumple x, que el conmutador de x y de y da x cuadrado, ¿no? Si no estoy equivocado.
Efectivamente.
Y si uno, no sé, ordena que y es mayor a x, te queda una base de Grobner. O sea, ¿ese álgebra es cosul cuadrática o estoy equivocado? Porque digo, y con x no se solapa consigo misma, ¿no? Entonces, te queda una base, de hecho te queda una base PW, ¿no? Andrea, bueno, igual seguro esta cuenta la hiciste en ese paper de alguna manera similar o sea, ¿cómo cambia
Es una extensión de Ocal, por eso tenemos una base.
y cómo, o sea, en el caso de hacer el approach con el twist y con la base PW, o sea, las cuentas que te quedaron, Pablo, son más cortas o...
No sé si más cortas, pero sí que son desde luego más elementales.
Es como más conceptual o no sé, como quieras decirlo. No sé.
No me atrevería a decir más conceptual para nada. Es un enfoque diferente. Son más elementales, o sea, es algo que un ordenador, por ejemplo, podría hacer. O es algo que tú podrías programar, ¿no? Por ejemplo. Sí,
Okay.
no me atrevería a decir más conceptuales, no, para nada.
Ok.
En el paper con Samuel, que en realidad ahí está x cuadrado, pero uno puede poner cualquier polinomio en x, como también Mariano había hecho con Max, y bueno, y la técnica y que son más o menos cosas que vienen de trabajos previos de Samuel con Georgia Benkart y Matthew Andrews. Así que bueno, tiene una descripción así muy detallada de las cosas que ya tenían ellos de antes.
A mí me quedó una duda cuando mencionaste lo de que tenés una fórmula explícita. Es tan explícita como el sigma que encontrás más arriba, ¿verdad? O sea, primero necesitas conocer explícitamente sigma y después...
Claro, sí, efectivamente. Sí. El sigma, si solamente viene dado y existe, entonces la fórmula no es explícita. Pero si el sigma es explícita, efectivamente la fórmula sí, se corresponde con él, desde luego. En el caso concreto de la resolución bar y las resoluciones de COSUL, sigma se puede encontrar explícitamente. O sea, existe, lo damos. Es este. Si en general las resoluciones son diferentes, entonces depende de si viene dado o no.
Ok, y el resultado es esencialmente agarrar la clásica fórmula de... digamos, esencialmente agarrar la... Gerstenhaber cuando define el corchete dentro del... usando la resolución bar, él tiene estas multiplicaciones sub i que dependen de poder meter ciertos términos adentro de otros. ¿Es algo así lo que obtienen a partir de sigma?
No, es muy diferente. Hay unas cosas que llaman, lo que Volkov llama homotopy liftings, que Negron y Witherspoon construyen explícitamente, ¿no? O sea, tú tienes tus resoluciones de COSUL y dicen, toma, estos son lo que Volkov después llamará homotopy liftings. Son extremadamente explícitos, no se parecen en nada a la construcción original de Gerstenhaber y con ellos son con los que construimos esta fórmula explícita. Es método completamente alternativo.
Bien, gracias.
Ok, gracias. ¿Alguna otra pregunta?
Sí, tengo dos preguntas. Una que me llamó la atención de que como ahí en rojo en la pantalla que se ve dice que la resolución bar satisface estas hipótesis. Entonces, si tenés dos álgebras A y B, y tenés la resolución bar para A y la resolución bar para B, y haces toda esta construcción y te da una resolución, unas fórmulas de corchete para una resolución de A tensor sub tau de B. Pero también tenés la resolución bar de A tensor sub tau de B.
Sí.
¿Te queda la misma fórmula?
No, te quedan precisamente relacionadas... Bueno, la fórmula será la misma cuando... Bueno, el resultado será el mismo cuando agarres cohomología. El bracket en cohomología será el mismo, pero la fórmula explícita viene precisamente por una diferencia de este isomorfismo.
Claro, no es canónicamente la identidad si pones la resolución bar en todos lados.
No. Y algo que sí que merece la pena mencionar es que, bueno, lo he mencionado, lo he así comentado en rojo porque el tiempo me apretaba, pero esto es un resultado, hay que demostrarlo, o sea, esto no es trivial, o sea, esto es como mínimo una proposición. Es algo que necesitas realmente pillar tus diagramas, ver cómo pasa dentro, o como mínimo tener un razonamiento. No es algo que viene inmediato por las construcciones anteriores de Shepler y Witherspoon ni de nadie.
Lo que pasa aquí, May, es que cuando haces cuando haces esta construcción con dos resoluciones bar, lo que te queda es como el producto tensorial de las bar de las dos, con la diferencial cambiada.
Exacto.
Y eso tiene tamaño más o menos la mitad que el complejo bar del producto tensorial.
La mitad. O sea,
Claro, porque el complejo, la resolución bar del producto tensorial es la diagonal del producto tensorial de las resoluciones bar.
claro.
¿No? Cuando haces el producto tensorial de dos resoluciones bar, te queda un complejo, un bicomplejo que es bisimplicial. Entonces puedes tomar la diagonal y te queda un complejo simplicial. Si lo haces con las resoluciones bar, la diagonal es el complejo bar. Pero si lo haces con la resolución bar y torces usando el cociclo, te da una cosa un poco diferente. El cociclo no, el twist.
Y la segunda pregunta es si cuando decís fórmula explícita, ¿es explícita o es una construcción inductiva grado a grado?
Es explícita. Lo que pasa es que tardaré unos minutos en escribirla, pero es muy explícita. Es larga, no es... sí, pero es explícita.
Pero
O sea,
digo, si quiero calcular el término 38, no necesito los 37 primeros. Eso sería...
No, para nada.
Gracias.
Gracias. ¿Alguna otra pregunta?
Pero o sea, podés hacerlo, pero en el proceso necesitas algo que tenés que construir, ¿no? Necesitas un morfismo de comparación o alguna cosa.
Pero vienen... lo único que usamos es el sigma, que viene dado, o en las resoluciones bar existe, lo construimos. Y
¿Cuál es el sigma?
Oye, el sigma, este sigma, sí.
Ah, ese, sí.
Sí. Y después usamos que Negron y Witherspoon en su trabajo encuentran estos homotopy liftings explícitamente. O sea, toma, es esto, que depende de la diagonal, efectivamente.
Claro.
Pero una vez que se tienen los homotopy liftings y se tienen el sigma, simplemente con la estructura de coálgebra del producto tensorial de estas dos resoluciones, damos la fórmula. No necesitamos ninguna construcción inductiva. No sé si eso responde a la pregunta.
Sí, la mía sí, gracias.
Ok, bien. Gracias. Entonces, ya María no apagó el micrófono, entonces no creo que vaya a decir algo más. Muchas gracias, Pablo. Y la próxima semana, entonces, tenemos la charla de Gastón.
Ok.